Let's take a few minutes to discuss synthesis strategies using alkynes. There is a figure in your textbook that involves alkynes going to alkenes, going to alkanes. I want to review that figure first, and then we'll get on to some synthetic problems. So we learned that we can partially reduce alkynes using H2 and Lindlers, or we can use sodium metal and ammonia. Both of those will get us from the triple bond to the double bond. And then, of course, we know how to reduce double bonds to single bonds. That's just H2 and palladium, or whatever your favorite noble metal is. So one question might be, how do we go in the other direction? How do we do this step? Or how do we take our alkene to the alkyne? I'm going to use a different color for these roots just to distinguish them. And we learned this technique in this chapter on alkynes. The first thing we would do would be to add a couple of leaving groups to the alkene. The second step would be then to add excess strong base. Basically, we're going to do a double elimination to form two new pi bonds. So the first step removes the pi bond, adds two leaving groups. The second step does a double elimination. And the third step, your book, I believe, shows water. Maybe you might use mild acid workup on account of the strong base that's present. So either one of these probably would work fine for the third step. So that's a way to take alkenes and temporarily reduce them or change them into the alkane, and then do a double elimination to end up back at the alkyne. And the steps here, taking an alkane to an alkene, that's going to be in the radical chapter. So you may or may not get to that during your exploration of first semester organic chemistry. You can certainly read about it on your own. If you do get to it, it'll be useful. If you don't get to it, it won't be necessary for future reactions. So we have a few different ways of changing the alkyne into alkene or alkane, and we can take the alkene and convert it back to the alkyne. Let's look at a few synthetic examples. So you might be faced with a reaction that looks like this. And from what we learned this chapter, this piece of the product is probably added as a in a nucleophilic attack chain extension. We've only learned one or two ways of creating CC bonds, and this is one example of that. And so we can look at this from two different directions. I could say, well, how can I add 4 carbons to my alkyne? And we know that the first step would be to deprotonate. The second step would be to add a 4-carbon alkyl halide, and we'd end up with this product. Be sure you're counting carbons, making sure that you don't lose a carbon, especially when we're dealing with alkynes. It's very easy to lose a carbon and not recognize that we have one here, or gain another one. So here I have 2 carbons from my original alkyne. Then I have 1, 2, 3, 4 from my 4-carbon alkyl halide. Another way to look at this problem would be to think about how to get this alcohol on the second carbon from the end. We've learned that in the additions to alkenes chapter. If I have an alkene on the end, I can add that alcohol pretty much just with concentrated sulfuric acid and water. That's all I need, really, to get that alcohol there. It is a racemic mixture, of course, because I have no control over stereochemistry in this case. So then, if you started here, the question becomes, how can I make this 6-carbon alkene from the alkyne? Well, maybe you recognize that there's 4 carbons that we can add. We added those 4 carbons, and now I have this 6-carbon alkyne. Seems to me there's only one step between these two, and that is a partial reduction. And because there's no stereochemistry associated with this alkene, it doesn't matter which of the partial reduction reactions we choose to use. So maybe I'll just write H2 and Lindlers here. If you wanted to use the dissolving metal reaction, you could do that too. Either one of them will get us this partially reduced alkyne going to the alkene. And there, I believe, we are done. This is a 3-step process. Add 4 carbons on the end of the alkyne, partially reduce the alkyne to an alkene, then add water in an acid-catalyzed hydration reaction, giving us the more substituted alcohol product. Here's another example of starting with an alkyne and ending up with a slightly more complex structure, both in terms of the carbon count and the functional groups. So it might be important to recognize that there are 5 carbons that we started with. It appears that we gained 2 carbons. Importantly, the functional groups are between these 2 carbons, which are just coincidentally carbons 4 and 5 in both of these numbering schemes. So this is probably where the alkyne was, because it's easy to turn alkynes into alkenes into dibromides. It'd be hard to move that along the chain and end up with our bromides over here. So most likely, I have numbered 4 and 5 in the same manner. This is indeed carbon 4 from the starting material. This is carbon 5 from the starting material. I probably need to add carbon 6 and 7, and I can do that because I have a terminal alkyne. So let's go ahead and deprotonate, and then add a 2-carbon species, in this case, ethyl chloride should do the job for us. And there I have my 7-carbon species. I've added 2 carbons to it. I still have some functional group control or a functional group handle that I can work with right here and hopefully eventually get to the dibromide. Let's think about the stereochemistry here. This is an anti-dibromide. We know how to add bromine anti, and it's just the Br2 addition to an alkene. So in this case, this is the shape of the alkene we'd need. And let me just have an aside over here. What if we wanted to make the cis bromide, the cis dibromide? Do we know how to add bromines syn to each other? I should call this syn, not cis. The syn dibromide. And I don't know how to do that. However, I can make this look like an anti-dibromide if I just do a rotation. And I can make this product from the corresponding alkene and Br2. So, as you see here, by choosing the shape of the alkene starting material, I can make it appear as though I added bromines anti or syn. I just have to correctly decipher what shape of alkene I should make. So let me wall this off. That's not part of this problem, but it could have been. And so we're going to use this E-alkene with bromine, and we're going to get the 1,2 anti-bromine situation. The question then becomes, how do I go from this alkyne to this alkene? This is an E-alkene. I need to reduce partly the alkyne. And to get the E, not the Z, I need the dissolving metal reaction. So sodium in liquid ammonia will get the job done here. So again, this is a 3-step process. The first step is to add 2 carbons to my initial alkyne. Then I partially reduce that alkyne to get the appropriate stereochemistry in the alkene, and that is going to be the dissolving metal reduction to get the trans alkene. And I can then brominate that, getting the anti-1,2 dibromide as my product. One final example here. We start with an alkyl chloride in this case, and we end up with, looks like a diol. And let's number our carbons again. 4 carbons. Looks like I have 6 carbons now, so I somehow need to make this bond between carbons 4 and 5. I have a leaving group on 4 here, so maybe an SN2 style reaction might do that. And I also need to be left with some functional group on carbons 4, 5, and 6, or near there, that I can eventually turn into the diol. As of right now, we've only learned a few reactions to make carbon-carbon bonds, and this is the alkyne chapter, so perhaps we could use an alkyne in this case. What if I took acetylene and deprotonated it and used it as a nucleophile to eliminate the chlorine. So a lot of students get stuck on this step. They don't recognize that they could just buy acetylene and deprotonate it and then add it as a nucleophile. That is perfectly acceptable. So don't be afraid to do that if you feel like you need to add your alkyne instead of create your alkyne from what we start with. And of course, this doesn't have to have 2 carbons. This could have 15 carbons. As long as it's an alkyne on the end, we can deprotonate the alkyne hydrogen and use it as a nucleophile. So I don't have to just add 2 carbons in this manner. I could add a bunch. But in this case, I've added 2. I've gotten my 6-carbon framework. We can then think back, how do we add a diol? Well, this is from the alkene addition chapter, so we need to have an alkene, and I need some form of adding a diol. There's actually 2 options here. OSO4 would add the diol, or MCPBA as the first step. Second step, mild acidic conditions with water as the nucleophile to open up the 3-membered ring epoxide that's formed with the MCPBA. And in this case, I can't tell that these OHs are syn or anti because there's no stereochemistry at carbon 6. So it doesn't matter which way they were added, whether they were added syn, as in OSO4, or if they're added anti, as in the MCPBA followed by H3O plus workup. So it doesn't matter. You might choose MCPBA and mild acid workup because, for one, MCPBA is dirt cheap. You can buy buckets of it. It's just a white powder. Acid workup is not hard. And OSO4 is toxic to the point of being deadly at certain concentrations. So this is an expensive, toxic gray powder that your lab manager, your boss, probably would prefer that you don't work with. So if we can avoid that, we would. And in this case, we can because there's no requirement for the OHs to be either syn or anti. So let's use MCPBA in this case. And then the last step is to take my alkyne and convert it to the alkene. We've done this before. This can be H2 and Lindlar's catalyst, or it can be this dissolving metal reaction, sodium in liquid ammonia. Either of these work. H2 and Lindlar's is probably easier. You don't have to get really cold ammonia and the pretty highly reactive sodium metal. But really it's up to you. So again, we have a 3-step process. The difference here is that we installed the alkyne by purchasing the alkyne and deprotonating it and using it as a nucleophile with our starting material, alkyl halide. So you don't always have to start with the alkyne or create the alkyne on your original carbon structure. You can buy the alkyne, deprotonate it, and use it as a nucleophile. Keep that in mind as you work more of these in class and on the future exam.